5. Okay, we ready? Ladies, you ready? Okay, so let's look at some new stuff today. We're going to look at some special parallelograms, right? So real quick, what's our definition of a parallelogram?
Parallel lines.
Okay, it's a quadrilateral with two pairs of parallel sides. Okay. Quick, what are some properties? So if we know we have a parallelogram, Megan, tell me one thing that we know about that parallelogram. What's one property of that? Okay, now that's the definition. I want a property. Well, once we know it's a parallelogram, I want to know something else about it. Something else, not the definition of something else. Somebody here, get us started, Duncan, and maybe you'll kind of see.
Like the two opposite quarters are like the angles are congruent.
Okay, so opposite angles are congruent. So if parallelogram, then opposite angles congruent. If parallelogram, something else. Opposite sides are congruent. Okay, something else.
Are consecutive angles like complementary?
Not complementary, supplementary. Good. So if parallelogram, consecutive angles, supplementary, and then the last one, if parallelogram,
then the diagonals bisect, right?
the diagonals bisect each other. Good. Okay, perfect. So we get 4 properties that come along with just knowing it's a parallelogram. If we wanted to prove it's a parallelogram, there are 5. There are 5 properties that we could notice that would show that it has to be a parallelogram. What are, somebody real quick, tell me how I get 4 of them. I mean, so how can I, so now we're changing it around. We're saying if this, you're going to fill in the blanks, then parallelogram. Okay, so if opposite sides are congruent, if, then parallelogram. If, in fact, all the ones you just told me, I could do the converses, right? I could flip all those around. If adjacent angles are supplementary, actually we have to be do a little more than that. Remember we said if an angle is supplementary with both of the adjacent angles, right, then it's a parallelogram. So that one gets tweaked ever so slightly. But essentially we've got the 4 properties of parallelograms that we can just do the converses to prove parallelograms, but there was one additional one. Yes, sir?
One pair of opposite sides is parallel and congruent.
Okay, good. If one pair of sides in the quadrilateral is both parallel and congruent, then we know it's a parallelogram. Okay, good. All right, so we're going to do something a little different today. Now we already know it's a parallelogram. So all the stuff we just talked about, we get to bring with us, right? But additionally, there are some kinds of parallelograms that are special and have some other unique properties. Let's have a quick look at that. So these are the other 3 special kinds of parallelograms we're going to talk about. So a rhombus, remember rhombuses from a couple years ago? So the definition of a rhombus is a parallelogram with 4 congruent sides. Okay? A rectangle. The definition of a rectangle is it's a parallelogram with 4 right angles. Okay? And then what about a square? So what about a square is unique?
All right angles.
Okay, so how could you categorize a square then?
Regular.
Okay, true. It's a regular polygon, but we could even do more than that. If we're going to break these into categories, we said we have quadrilaterals.
Is it a regular?
Yeah, but we break up quadrilaterals. We've got a subset of that called parallelograms, right? All the quadrilaterals that have opposite sides parallel. And then within the parallelograms, we've got a subset of rhombuses, right? Where all the sides are congruent. Oh yeah, square falls under both of those, doesn't it? A square is both a rhombus and a rectangle.
But not all rhombuses or rectangles are squares.
Exactly, right. And so if we had to represent this,
Not all squares are circles.
true. So if we had to represent this with, remember Venn diagrams?
Oh, yeah.
Okay, set diagrams. Venn diagrams are useful. So if we have a Venn diagram here where we've got the set of all quadrilaterals, And then we're even gonna look inside that, we're gonna say, we're just gonna look within the subset of quadrilaterals that are parallelograms. So we can have other quadrilaterals that aren't parallelograms, obviously, right? But the ones that are could still be divided up. A subset of parallelograms are rhombuses. So is this sometimes, always, or never true? The next few questions I'm gonna ask you all have either the answer, sometimes, always, or never. You have three choices. Don't say it out loud. A rhombus is a parallelogram. Cassie, is that sometimes, always, or never true? A rhombus is a parallelogram. What do you think? Can you think now, how can we approach this? Can you think of an example of a parallelogram that is a rhombus? Well, I mean, something like both of those would be, right? So we can think of at least one example of a rhombus that is a parallelogram, so the answer is not never, right? It's at least, it's sometimes or always. How could I distinguish between which one it is? In what case would it be sometimes? Okay, good. If you could find an example of a parallelogram that is not a rhombus, then the answer could only be sometimes, right? Does that make sense? Because I thought of an example of a parallelogram that is a rhombus, and maybe an example like this that is not a rhombus, where all four sides are not congruent. So what's it have to be? Sometimes. A rhombus is sometimes a parallelogram.
Wait, isn't that the other way around? A parallelogram sometimes.
Oh, sorry, other way around. A parallelogram is sometimes a rhombus. Okay, so what's going to be, now what's this one going to be? A rhombus is sometimes, always, or never a parallelogram. Always, yeah. And how come? Because the set of rhombuses is completely contained.
Jesse is just too smart.
No, that was good. Good. Did I said it, the first time I said parallelograms and
No,
rhombus.
you switched it every time.
You switched it every time you said it.
I did?
Yeah.
Okay. What? So let's be clear. Okay, so let's be clear. So a parallelogram is sometimes a rhombus because some parallelograms are not rhombuses, right? But a rhombus is always a parallelogram because all rhombuses are parallelograms, right? In other words, the set of rhombuses is completely contained inside the set of parallelograms, right? Okay, how about a rectangle is a parallelogram? Sometimes, always, or never? Always. Okay, Matthew, a parallelogram is a square. Sometimes. Okay. How about a rhombus is a square, Kirk? Sometimes. Okay, Lily, a square is a rectangle. Always, right? Because the set of squares is completely contained inside the set of rectangles. How about this one? A square is a rhombus. Always. Okay.
When is never going to be used?
Okay, how about this one? Well, I gotta think of one. Okay, here's one. A rhombus is a circle.
Or rhombus is a triangle.
Or a rhombus is a triangle. Yeah. Okay.
Wait, is a rhombus a rectangle?
Yeah, if it's a square,
Oh.
right? Okay, so you get the idea?
A rhombus is two triangles.
True.
So is a rectangle and a square.
Okay, so have a look, please. Here we go. Okay, so if we know that a parallelogram is a rectangle, then we know, well, we already said this. We already know all the stuff that goes with a parallelogram is true, okay? But there's some other stuff that we have kind of a special relationship with. Look, for example, let's take a second to look at the rectangle corollary. Now, I want you to tell me what's different about this. A quadrilateral is a rectangle if and only if it has four right angles. Okay, is that the definition of a rectangle? It's a little different. You go back. how do I go back? Over here. A rectangle is defined as a parallelogram with 4 right angles. Okay, what's different about the corollary? Ah, look at that. Is that a misprint, or does that seem important?
Yes.
Maybe it doesn't seem important, but it is. It says a quadrilateral is a rectangle if and only if, and remember what that means. If we say if and only if, what's special about if and only if? It goes both ways. It's biconditional, right? So we can start with either one of those two parts of this statement being the hypothesis, and the other one could be the conclusion, right? So we know that if a quadrilateral is a rhombus, then it has 4 congruent sides, right? If a quadrilateral has 4 congruent sides, then it's a rhombus, right? Did we need to show that it was a parallelogram? No, we didn't have to. How could you kind of visualize that? So we could say maybe like this. So we're starting off with quadrilateral. And let's say, so let's go the other way. I'm gonna do it the other way. Let's go this way. Let's start off with, a little easier to see, with it being a rhombus. So if it's a rhombus, then we know it's also a parallelogram. Right? And we know that if it's a rhombus, it's a parallelogram with 4 congruent sides, right? Okay. Do we need to go through the parallelogram part, though? Turns out we don't, right? We can bypass that. Why is that useful? Well, we don't ever have to show, if we're trying to, for example, in a proof, we're given that a quadrilateral has 4 congruent sides. We don't have to go through the intermediate step of showing that it's a parallelogram first. Even if we don't already know it's a parallelogram, we can just immediately go straight to the fact that it has to be a rhombus. There's no other way it can be, it turns out. Why is that? If it's got 4 congruent sides, can anybody justify that? How can we automatically skip the notion that we have to consider it a parallelogram? Well, that's not what I'm getting at. If it's got 4 perpendicular or 4 congruent sides, right? What does that mean? It means that, right? Could you easily show that it has to be a parallelogram?
Yeah.
Right? Is there anything else it could be? No, right? Because we know that's one of our, remember our statements we just looked at? If, fill in the blanks, then parallelogram. Wasn't opposite sides are congruent one of our fill in the blanks? If opposite sides congruent, then parallelogram, right? Make sense? It could be, but a square is a rhombus, so it's still a true statement, right? Does that make sense? Yep.
So rhombus can only have 4 sides?
Yeah, rhombus is, by definition, a rhombus is a parallelogram with 4 congruent sides, right? But you see how we can do this? If we know we've got just a quadrilateral with 4 congruent sides, automatically it's a parallelogram. We know it's a parallelogram by the properties of parallelogram, so we can skip the middleman and just say it's a rhombus. Yep.
So if you have a quadrilateral and it's got 4 congruent sides and 4 congruent angles, can we bypass both parallelogram and rhombus, or parallelogram and rectangle, and just go straight to square?
Yes, we'll take a look. I'm glad you brought that up. No,
Just clarifying things.
you can't. So yeah, let's quickly look at the rectangle corollary then. A quadrilateral is a rectangle if and only if it has 4 right angles, right? So same kind of thing, I guess I kind of jumped around. That makes sense, right? Because if a quadrilateral has 4 right angles, how do you know immediately that it has to be a parallelogram? Because if what? Then parallelograms. What applies here?
Opposing angles.
If opposite angles are congruent. If they're all right angles, they're all congruent, right? Opposite angles are congruent. So it's sort of implied it's a parallelogram, but we don't even need to bother with it. We can just skip that step because it's sufficient for us to know that it's got 4 right angles. If it has 4 right angles, skip the middleman and just, it's a rectangle. We can get more specific immediately, right? And then Elton's point also works. If a quadrilateral is a square, is a rhombus and a rectangle, then you can skip the fact that it's a parallelogram and just say it's a square. Yes?
So will these be on the sheet?
Yeah, I'll add them to the sheet. Yeah, yeah. Yep.
What real-world applications does knowing how to prove that shape is a certain geometric figure?
It's got a ton of real world. I mean, I'm not going to list them all for you, but like a really complicated example, a very, very complicated example would be that in a much more complicated branch of mathematics called topological math. Topological math has to do with properties of objects that are retained even if the object changes its form dramatically. So for example, topologically, what are those fancy frisbees with no middle called? You know,
Yeah.
like the ones that don't have their hollow in the middle,
Oh.
like is it a Aerobie or something like that?
Yeah.
So you know, like an Aerobie? Okay, so an Aerobie and this coffee cup are topologically similar. How come? Because they each have an open loop. And so would you agree that if I like melted this thing and I reformed it, that loop could never close, but I could push some material around the other edge of this and flatten it out and make an Aerobie out of it? You kind of see that?
What?
Yeah, but I mean, I might have to like kind of form it around so I could.
You might have to change the material.
Wait, if you
So
melted it,
it
the loop would go on.
doesn't break.
Okay, I mean, you get the idea though. Pretend this, okay, let me say this differently. Pretend this cup is made of like clay, right? But it's not hardened clay. It is, but it's not hardened clay. But pretend that if I wanted to, I could like have a pencil stuck through this thing. So the pencil's always gonna be inside the loop, but I could push some of the clay, kind of squeeze it around the other side of the handle and expand it and flatten it out and make an Aerobie shaped thing out of it. Right, would you agree? So even though they're dramatically different looking things, because they each have one closed loop as a part of their volume, because this isn't a closed loop, it's got a bottom on it, right? They are topologically similar shapes.
So if it had a hole at the bottom, it would also be.
Then it would have two, then it'd be something different. Then it would have two open loops, and it would be related to a whole different class of topological objects, right?
Is that always both have open loops? They're similar?
Yes, they're similar.
What if it was a mug without a handle and then you melted it and flattened it?
Okay, well then, you're right, then I'm changing it. Then I'm changing its topology, because I'm adding a loop that wasn't there. Why do I bring this up though? Okay, this is weird, but the question was asked, why is it important to be able to classify shapes?
What if we
Now I'm
don't want to
regretting
go into that? Yeah. Then what used to happen?
Okay, I've always got, in all seriousness, I've always got my fallback answer on this, which is the best one anyway. Listen. Okay, so this is why this is all important. Even if you don't ever go into math, which is possible, I hope you'll take more math. But even if you never do it, it's really valuable because math is the only truly abstract language that we have, right? And I think I gave you this example earlier. This is a little strange, but physicists, I mean, the smartest guys, like the dozen or so people that can really understand the ramifications of string theory and cosmology, the whole world. These guys have a lot of intuition. And when they look at multiverse theory, and they look at all the different branches of multiverses that could exist, so, and there are an infinite number of different configurations the universe could really take, but in any conceivable configuration, if you had a sentient being that could study math, this is the conclusion they come to. that it doesn't matter how many dimensions exist in your universe or how many dimensions of time there are, or any of that stuff. If you sat down and studied math, would it be the same or different than the math you're studying? Ultimately, it's the same. They might start at a slightly different place, but if you keep going with math, math embraces spaces of all dimensionalities. We're looking at a very finite bit of geometry. We're looking at Euclidean geometry, which is a flat surface in a three-dimensional space. But you can easily dovetail on that, and you can look at geometry of different dimensionalities, and it's not that big a deal, really. I mean, it's, if you take years and study it, I mean, it would be, and you might, then it's totally understandable. You can't always visualize it, but the math is there, right? You can look at a, arbitrary number of dimensions in math, and it's not that big a deal. I mean, the math still explains it and takes care of it. So people in this other bizarre universe, when they studied math, it would be the exact same math you're studying. That is huge. Think about that. That just gives me chills. Think about that. That tells you that math is the only thing that transcends even the universe we live in. It couldn't be any different. So math is not, it's not created, it's just uncovered or discovered, right? It already exists. It's just there. Yes?
Did you learn all this or you just?
This stuff?
Yeah.
Well, I mean, it's honestly, it's what intuitively I would think that would have to be the case, but people that are smarter than I have said that also, and that's kind of why I say, okay, well then I can hang my hat on a little better if someone else is saying it. I mean, it makes sense to me that it would be that way. But so that's pretty amazing. Think about that. And is it real at all? There's nothing we ever do in math that is remotely real. None of it exists in the real world, and yet it's descriptive of everything. In any possible universe, it describes the universe perfectly, right? So that's a pretty good reason for studying math, I think, right?
Is there a fourth dimension of geometry?
And my coffee cup thing. So why did I bring that up? Well, these physicists that study the universe probably, to the best degree we can quantify it with physics, the best candidate for an absolute model of physics is string theory. String theory is really complicated. It exists with 11 dimensions, not just 3 dimensions in time. It's got 11 total dimensions, 3 of which are big and normal looking, but the other spatial dimensions are just tightly curled up, and they're actually, string theory would say, they're out there right now. I mean, you just can't, they're so tightly curled, and they're warped on such a small distance scale that you can't see it, but they're there. And the math that they do in string theory to try to understand and predict things like gravity, to try to build a model where mathematically something would pop out of that looks like gravity, and they've done this. But in order to do that, in order to be able to take this very complicated mathematics and make gravity show up in the equations, and make electromagnetism show up in the equations, and make time flow in the right direction, they've got to do a lot of this stuff where they've got to take, there's like a 7-dimensional space that's a subspace of our universe called the Calabi-Yau shape. And these things, you have to morph them around. You have to do things like turn that coffee cup into an aerobic, stuff like that. You have to go through these changes in order to make things show up. And so, you can get as simple or as complicated as you want to, but the idea that what we're doing here is all the way through. You got to be able to recognize the characteristics of a certain kind of shape, whether it's a 2-dimensional shape or a 7-dimensional shape. You still have to know what the characteristics are so you know when you see it. Does that make sense? I mean, kind of a long answer to a short question, but you should know better than to ask me a question and not expect a long answer from
I'm
it.
sorry for causing all this.
Thank you very much.
We're not going there yet.
Please don't hurt me.
Please don't hurt me.
Okay, so anyway, here we go. Back to business here.
I guess it went out in the end.
Okay, so we can use these shortcuts, right, to prove that quadrilaterals are a rhombus or a rectangle or a square without having to go through the parallelogram middle step. Okay. All right. What else? So how could we do this then? If we know that this is a really simple example, but let's just look at the logic behind this. If we know that a quadrilateral or even a parallelogram is a rhombus, how could we use that information to solve for y?
So the sides equal to each
Yeah,
other.
because I know if it's a rhombus, all the sides are congruent, and so the side lengths are equal, right? So I get some additional information that allows me to set up an equation, right? Do you get that? Okay. All right, so just in general, that's, these additional properties are going to be very useful. Okay, we get a couple more that have to do with diagonals. So we know that if the diagonals of a parallelogram intersect at a right angle, so if the diagonals are perpendicular, then we know it's a rhombus, guaranteed. That's a property of rhombuses, right? So we can say if the diagonals are perpendicular if and only if it's a rhombus. It goes both ways, right? We also know perpendicular diagonals go with rhombus. We also know that if the diagonals bisect the opposite angles, it's a rhombus. That only happens with a rhombus, right? So once again, we get this if and only if statement. We love those because we can flip them around, right? They work in both directions. We get a lot of mileage out of them by conditional statement. Rhombus, if and only if diagonals bisect opposite angles. You understand what that means, right? So the diagonals, when they intersect angle A over here, it's going to cut it into two congruent angles every time. Okay?
It doesn't do that with the parallelogram,
No, it doesn't do it with the parallelogram in general. It doesn't do it with a rectangle. It only does it with a rhombus. Yep.
What about kites? Doesn't it do the same thing?
Okay, okay, yeah, but we haven't talked about kites yet. So yes, there's almost, not exactly, only in one direction. Okay, but we'll get there. Okay, we also know that if the diagonals are congruent, then it has to be a rectangle, right? So rectangle if and only if congruent diagonals. Okay, it goes both ways. So we could set up, there's a whole bunch of different, that opens up all kinds of different avenues for us to solve for a variable, that doesn't it? Like if I had in here, if we just knew this was a parallel, if we knew it was a rectangle, and I had something like this, if I had, what is this thing supposed to be here? This is AC, so if I had like AC equals x squared plus 3x, and BC equals negative x minus 12, negative 2x minus 12. What could I do to solve for x? If it's a rectangle, what do I know about the diagonals? Oh, did I not? Oh, whoops, I'm sorry. Gosh, that's supposed to be a BD. There we go. Now how about it? Sorry. Then they're equal, right? Okay, I wouldn't have had that if it's a parallelogram, or if it's just a plain old non-specific parallelogram, or if it's a rhombus. Those aren't true, and I maybe can't solve for x, at least not easily. I've got to figure out something else maybe, right? Go through a bunch more steps, maybe have some additional information. But if it's a rectangle, I've got an easy way to solve for x. I've got another relationship that I can turn into an equation, right? You get that?
Wait, how will we be able to tell that it's a rectangle or say it's rectangle?
Yeah, usually it's going to be one of two ways. Either you're going to be told directly that it's a rectangle, or you're given some other information that means it's a rectangle, right? Okay. Okay, so, okay, we already talked about that. Okay, so this guy. Now we're done with this. So let's try. Get out your notebooks. Put them up. Let's see if we can prove this.
Wait, where's what?
So we're gonna prove one of those relationships that I just showed you. If we're given a rhombus, we want to prove that the diagonals. So I gotta write them in, don't I? The vertices. So the vertices are A, B, C, D. So we got to prove that the diagonals are perpendicular.